Yeah, welcome to the session, Emerging Energy Water Nexus Research and the National Alliance for Water Innovation. My name is James McCall, and I am a senior analyst with the National Renewable Energy Laboratory. I've been here almost 7 years, and during that time, I've worked on different energy water nexus research objectives, along with some oil and gas water sustainability. And since basically the start of 2020, working with the NREL Water Hub. So today, just going to kind of go over the hub itself. After our first year and a half, we have some kind of exciting research results to kind of share, and then we'll kind of go into some other kind of discussions of why climate change and kind of the race to zero actually matters to the National Alliance for Water Innovation. So just first off, just some kind of quick disclaimers. Just want to acknowledge that this, everything in this presentation was funded by the U.S. Department of Energy, in particular the Advanced Manufacturing Office. So kind of why was NREL started? Started with in mind with that non-traditional waters are geographically widespread and can contain valuable constituents, but are either discarded or ignored. And so the Department of Energy and some other stakeholders thought that kind of new desalination technologies could economically treat these water sources and could kind of come up with a resilient, cost-effective water supply for the 21st century. Along with some other kind of like water resources, there's also the express intent to reduce the energy intensity of water and therefore reducing the cost. So what is NREL? It is a research hub made up of a lot of different partners, kind of across the country, as you can see, made up of national labs, universities, and then a lot of other private entities who kind of join the consortium throughout to kind of either submit or to participate in the research objectives or to kind of have some funding opportunities. If there's any interest kind of during this talk or afterwards, you can go to nrehub.org there at the bottom, and you can become a member, and you can also get a lot of access to a lot of really interesting kind of research results. And they also are releasing kind of funding opportunity announcements for technology development. So it's a $110 million hub over 5 years, focused mainly on early stage research, so TRL 2 to 4. And it's looking at kind of transforming kind of linear water treatment systems into circular water treatment systems. And to do that, we are evaluating 9 different alternative source water types for 5 different end users that I'll go over here in a bit. And so kind of for this presentation kind of ended up chatting about kind of what are some of the climate impacts on the NREL mission. And so kind of what we kind of came up with was, some indirect emissions of methane and nitrous oxide that kind of occur during the biologic treatment process. And also some, basically anytime that, contaminants are actually released into water resources, there is the impact for, or impact on the environment. Second is that we see that there is the potential for using kind of these brines of the source, these water sources as a source of alkalinity and carbon sinks for carbon sequestration, and particularly as we're kind of seeing some in California, kind of the looking for kind of a water source to actually sequester this carbon is going to be a huge issue. And if there's a way that we could treat water economically and then kind of provide it to this would help for that objective. We're also looking at comprehensively characterizing energy intensity and the associated carbon intensity of water treatment technologies. And this is anywhere from electricity inputs, fossil fuel inputs, and also chemical inputs. And so trying to kind of, if we can kind of establish that baseline, then we can kind of have a mark on which to measure ourselves against and kind of how we kind of then kind of define those improvements. We're also assessing the potential flexibility of water treatment systems to participate in demand response programs. And so this is in particularly in a high share of renewables on the electric grid. There are going to be times where there are both excess electrons, and then there's a time where there's going to be a need for more electrons. And so if we can shift, either treatment or pumping or other kind of loads, then we can actively participate, kind of reducing our energy cost and also kind of providing some services to the grid. So there's some kind of research on that, and it's kind of the NOW mission is really trying to kind of develop technology that'll actually make this possible, not to kind of actually explore those opportunities. And then also just, examining trade-offs of emissions of electrified processes, kind of replacing chemical inputs. So we can kind of electrify the emissions, and we can kind of take advantage of an increasingly renewable grid, and kind of offset some of those fossil fuel costs in the chemical inputs. So again, why does this matter for Race to Zero? So, we see, particularly in responding to drought and other kind of water availability changes, we can see an increased use of non-traditional water resources as a climate mitigation. And this might be a little counterintuitive, because right now, kind of non-traditional water resources can often require 5 to 10 times more energy to actually treat. And so we have this kind of trade-off of, we need water and we have excess electrons, or, we can kind of take advantage of declining costs of technologies and declining energy intensity to kind of create some other resources. And kind of an example of this is that we've seen, SB 1284 in California was basically looking at, kind of some reporting requirements to actually kind of look at, are there ways to, or I'm sorry, SB 1281, ways to look at oil and gas water reuse. And so basically kind of this resource that is generally just kind of pumped down whole after it is used, it's kind of considered a waste. Is there a way to kind of identify opportunities for that? And I'll go into some of the issues with that later on. Really a balancing act between the current water system and the future. So it's just kind of, how does our current infrastructure and kind of treatment respond to a changing grid? And this kind of also goes, in with some reduced energy and chemical inputs from optimized treatment systems. And then kind of really the water system has a large role in these net zero carbon goals. Oftentimes, electricity is, a lion's share of both the expense at water treatment facilities, but then elsewhere, for these non-traditional water resources, they're often just geographically diverse. And so how do we kind of take advantage of all these resources in this area to kind of benefit both the electric sector and the water sector? So they kind of play hand in hand there. So what we've kind of seen from kind of some of our outreach is that users really expect water challenges to grow. They're really not, users are not concerned that they can operate, but they really, it's the lack of a sufficient reliable water supply that can reduce, some opportunities along the way. And so it's not really a threat to them. It's more of like a lost opportunity of like, why am I pumping this water down whole when I could find some other use for it? There are also things of water quality challenges, such as evolving, such as PFAS, microplastics, and selenium for certain kind of water sources. Next is that brine management, and particularly from reverse osmosis and current kind of other desalination is a major challenge. Like, we're gonna have to figure out how are we going to valorize these salts, or how are we going to reduce this brine, and particularly we've seen in the oil and gas sector induced seismicity issues and so on and so forth. And so this is really a big kind of, how do we close this salt cycle? And in particularly, if we start desalinating a ton of water, we're going to have another waste stream that we're going to have to deal with, or potentially value stream. Any of these solid technologies really need to work with existing infrastructure. We have put a lot of investment into our infrastructure and the water system. And so how do we kind of develop technologies that are new and innovative while still kind of playing with our current systems? And then institutional barriers can slow the technology adoption process, both from a management perspective, also, but from a regulation perspective. So how do we kind of ensure that some of these technologies are actually safe to use and cost effective, and kind of go down that path? And so to answer some of these questions, we leverage a diverse and multidisciplinary team to tackle these questions. We have 11 different university professors as cartographers. That's basically people leading some of our initial baselining and road mapping processes that I'll go into here in a sec. We have a lot of support from national labs and universities. We, kind of surveyed 24 different kind of systems as a baseline, and I'm sure that we probably talked to some folks on this call about their system or anything else. And then we really kind of we got roadmap input from over 300 plus external contributors in these activities, and a lot of these people were researchers, water end users, and water industry reps, and so kind of just trying to get like a really good understanding across the industry of what is needed and so on and so forth. And so what is the road mapping and kind of baselining process? So really, as you can see in the left on this diagram, we have kind of the cost of the current industry practice. And so we are not trying to compete with the current industry practice. We're really trying to compete with the marginal cost of the next option. That is kind of the if that next resource that is needed, if we need more water resources actually goes away, we actually want to compete with that. We don't want to compete with the existing industry. So this is really more about kind of this forward-looking kind of thought, and kind of then, and they call that marginal cost pipe parity. And so we're taking a look at where we are currently and the current industry approaches, what new technologies must be developed to actually achieve and to kind of compete with that next water resource. And then the roadmap is really, how do we actually get to where we want to be? And so kind of this is kind of where a lot of the R&D dollars are being put, is to kind of see kind of, if we can kind of take a little step on, sourcing, transport, pre-treatment, treatment, and kind of just take a little chunk out of each of those, we can eventually kind of get closer to this cost-effective water treatment for these non-traditional resources. So there's different pipe parity metrics that we looked at, levelized cost of water, energy intensity, the use of alternative energy and water resources. And so that's basically just taking a look at the renewable aspect and kind of the different sources, and also water intensity and system resiliency. And so really kind of along this process, we're looking at kind of some different areas. And so we're looking at autonomous operations. So how do we develop sensors and process control? We're looking at precision separation. So kind of how do we actually target removal of these trace solutes for advanced water recovery, and kind of really how do we kind of ensure that treatment aspect is there? Resilient treatment and transport. So basically, can these be off-grid systems? Can they be small? Can they be closer to their end users? Can they be closer to their source? So on and so forth. Kind of how do we reduce the brine, as I kind of mentioned earlier, and so kind of taking a look at these technologies that can kind of displace thermal distillation and kind of other materials research. We have modular membrane systems. This is really on the manufacturing side. So can we kind of mass manufacture these systems and kind of then deploy them? And then we have electrified treatment processes. This is really about can we kind of electrify this? And then overarching this, there's actually a kind of a circular water economy. So how do we actually make sure that once we actually do treat this one, that there's a way to sell it and to kind of get it to its end users? And kind of along the way, and particularly I think for this modular membrane systems, it's now itself is targeting kind of small scale, kind of fit for purpose treatment. But along the way, there are a lot of opportunities for these technologies and these improvements to then be incorporated in decentralized water treatment systems. So it's not really we're looking to kind of compete, or these technologies are not looking to compete, but it's more like, how do we kind of, how does the high tide raise all the boats? And so, as I mentioned earlier, we looked at 9 different source waters, and they came up with a catchy acronym of IPN Campus, which, as you can see on here, someone had a sense of humor that day. So it's taken a look all across from, industrial, brackish, municipal reuse, and particularly how do we enable that, conventional and unconventional produced water, so kind of from the oil and gas operations, agricultural runoff, mining water, power, and particularly thermoelectric cooling water, and then also kind of desalination for seawater, more traditional desalination technologies. So we have all these, and basically we have 9 baselines that we developed. And baselining, kind of we start with, we're first going to characterize a treatment train, and so kind of on the right, I believe, is a municipal water plant in operation, and so we kind of take a look at the typical conditions, technologies, multiple configurations of these different case studies per source water, and then a geographic and subsector diversity. So how do we kind of take a look at or at least get like a snapshot of the current industry, knowing that's not going to represent every kind of use case, but can we represent most of it, and kind of make an informed decision based off that. Then after that, then we end up using kind of a techno-economic analysis tool we developed called WaterTap 3, and that's basically taking all this data, and then we kind of develop those, kind of a baseline for those pipe parity metrics, and can kind of break it down by process. So in this one on the right, the main cost of water is the principal treatment. And so it's basically trying to identify here are these actually areas that we should target to reduce the cost. And then basically after that, then we use those results and we put that into our roadmaps and kind of perform some sensitivities to basically look at kind of if we make a change at certain areas, like kind of what impact is that? And then that's another way to get more fine tuned on kind of where is it that we wanted to kind of focus for water treatment. This is then organized into 5 user roadmaps. Basically, and then these are all available. So we have kind of source water baseline studies that takes a look at these 9 different kind of source waters and kind of what is the current state and what is, you know, some of the research in there. Then we have 5 water user roadmaps. And so basically this is for each individual area that I had on this previous slide, you know, for power, resource extraction, industrial, municipal, and agriculture, kind of what are the technologies needed to allow for the reuse of those non-traditional water resources. Then after that, then that's all summed up into one master roadmap that then kind of synthesizes all these outcomes across the 5 different water sources and really kind of characterizes here are the different areas that we need to focus on. And so there's a lot of text amongst these 15 different areas. And so kind of depending on your interest, you can go and kind of take a look and kind of do that or take a look at what actually interests you. As I mentioned earlier, this is all available at nowehub.org. And again, we are always looking for partners to participate. So feel free to go on there and check out our resources. So next, I'm just going to go over some kind of like high level findings. I'm not going to go over each and every single one of these. We would be here much longer than the 25 minutes that I have. But basically just showing that kind of like across these, you know, 7 different areas, we came up with roughly 18 different kind of things to focus on. And so kind of just like as like an example for, you know, I'll go over an example for 2 of them for, you know, so for the electrified treatment process, they want to take a look at treatment process electrification. It's pretty self-explanatory, but basically like, is there an electrochemical process for contaminant removal or reagent production, basically to try to remove some of those chemical inputs and to also allow for the water industry to kind of take advantage of a lot of the kind of the changing and kind of renewable grid. We also want then agile treatment trains for intermittent and variable operation. So we have seen, you know, is there a way that we can support load following and kind of demand response services through these materials? We'd end up taking a look at, you know, is you know, if you run a reverse osmosis system with kind of an ever-changing electric input, you know, is that going to cause, you know, impact over the life of the system? Is that going to cause some treatment train inefficiencies? And basically trying to kind of define that the window in which we can kind of play with. And so there's really a lot of questions for this. There's a lot of concerns, but it's basically trying to take a look at that and to enable that. And then next we have, you know, the circular water economy, and this is really kind of how do we get water from where it currently exists in, you know, its kind of non-traditional kind of waste form, and how do we transport that, or how do we treat that into a different kind of end use? And so this is really at what scale and where should these different treatment technologies actually be deployed? And so it's really develop systems and models to optimize distributed water treatment networks and configurations. And so, you know, what is going to work for a user kind of right on the ocean is not going to work for someone in the middle of West Texas, and vice versa. And so kind of like, how do we actually both map those resources and then also kind of identify an end user for them? And then really quantifying the benefits of A prime for distributed and centralized systems. And so kind of you know, again, it's defining this structure that can be used at multiple different sites across multiple different locations, and not this like one size fits all kind of approach. And then so kind of I think initially one of my prompts was to kind of talk about some, you know, what are some regulatory issues across roadmaps. and or just kind of for the National Alliance for Water Innovation and in general. And kind of some regulatory issues that we're seeing is, you know, overall we're seeing kind of a public health. So how do we ensure that these new treatment technologies can treat the water to the correct purpose, and how do we also communicate that? I mean, I think we've seen that with oil and gas water resources, and particularly within use on crops. You know, there was a big public backlash against that. You know, kind of has enough science gone into this? You know, can we ensure the public that kind of what they're going to use is actually safe to them? We also have environmental health, and so this is much more about reducing the emissions. And also just kind of a changing, you know, in environmental health guidelines that I think particularly around PFAS or kind of these emerging contaminants. And then also kind of water rights. You know, in particularly in certain states, we have seen, you know, as you kind of take this product that was a waste and now kind of define it as a resource, there is kind of some issues with who actually owns that water. And you know, because some of my background is in oil and gas, you know, the people own rights to the oil, but they might not own the water rights, or they might not own the land rights. So there's kind of a big issue about if you take this waste and make it that, you know, that's the who actually owns that water and who should actually be paid. And so there's some certain things that need to be kind of discussed to enable that. On the power sector, we are seeing kind of some restrictions on disposal, and then also water ownership issues. From the disposal perspective, you know, the EPA has updated some of its thermal regulations, and kind of it's limiting the use of certain treatment or cooling technologies, which inherently kind of reduces the amount of water that's actually available from the power sector. But it's more of a consumptive use versus just putting the hot water back into a stream or kind of the water source. And so there's some issues there. Is that if we want to use this resource, are the regulations actually going to interfere with that? For the resource area, which is oil and gas and mining water, there's really, like, as I mentioned, there's a huge public acceptance issue. And you know, and basically this regulation evolution to keep up with technology development and kind of contaminants, and you know, particularly in the oil and gas sector and the mining sector, we are seeing contaminants that are never going to pop up, you know, or not never, but very rarely kind of pop up in the municipal sector, such as, you know, naturally occurring radioactive material, the extremely high salts, you know, 300,000 plus TDS and so on and so forth. And so kind of that again, how do we ensure that this is a safe kind of process throughout this? Industrial water, and this is mainly kind of how do we enable reuse within the facility, and then also kind of match users to this end use. So it's like, can they take advantage of this certain characteristic? But there's really a public acceptance issue here, but then also workforce training. So how do we make sure that these, you know, this different operating paradigm of I'm just going to just dispose of my water, it's going to require a lot of sensors and trainings and a lot of just like really a rethink of how we operate the water sector, and you know, in different areas. And on the municipal side, we were seeing kind of conflicting local, state, and federal regulations, and this is both on the discharge, but then also on the emissions and kind of carbon reduction side. You know, there's a lot of differing kind of viewpoints that kind of occur within this, and kind of managing those can be very complicating, and particularly for you know, for the water sector, they have a lot of water experience, but they might not have a lot of energy experience. And the energy sector might not have a lot of water experience, and vice versa. So how do we kind of make sure that those kind of regulations at least are somewhat in alignment? And then it's the same with agriculture. Basically, there's a lot of land rights issues in local and state and federal regulations. So that was all I had. I thank you for your time. And again, please go to nowihub.org, and if you're interested, and I will look forward to being on the panel here in about 35 minutes. So thank you so much.